Good morning. My name is Jon Fryzek. I'm with a company called Epidstat Institute. It's a small consulting firm. Before I was with Epidstat, Institute, this is kind of my life. I was born in the middle of the country. After university, I went to rural Africa and taught maths and science. Then I went to University of Michigan. I did my master's work in Kathmandu. After that, I went to the International Epidemiology Institute, and that's where I did my titanium dioxide studies. I did a lot of occupational studies there. Rocket engine workers, aircraft manufacturers, a lot of different groups like that. After I left the International Epidemiology Institute, I went to the pharmaceutical company, and then about 5 years ago, I formed Epidstat. So we're a small firm in the US, about 18 of us. So today I'm going to give you just a broad overview of epidemiology, in particular occupational epidemiology and the type of study designs and analysis you do in that. Then I'm going to talk mostly about my study because that's the one I know most about. And then at the end, I'll go over the European and US DuPont studies and then some general conclusions. Okay. So the first slide, what's epidemiology? It's really the study of the distribution of diseases and causes. And by distribution, I mean understanding diseases and causes in person, place, and time in human populations. So this is just a picture of populations. The purpose of epidemiology is to understand the cause of disease in humans. And the relevance is epidemiology is one of the only disciplines that provides direct evidence of associations between diseases and exposures, such as workplace chemical exposures, in humans as they exist in real life, not in a laboratory setting or a controlled environment in animal studies. There are two types of studies, cohort and case controls. I'm going to focus on cohort studies because that's mostly what occupational studies are. This is just kind of the classic diagram of epidemiology. You look for the relationship between factors and outcomes or diseases while controlling for different confounders or effect modifiers. These are kind of nuisance factors that you want to control for in your relationship. So there are three components to occupational epidemiology. There's surveillance, which in surveillance epidemiology, you're just trying to identify diseases by different categories of workers and looking for early warning symbols or signs of occupational hazards. Hypothesis testing, that's what we did with our titanium dioxide studies. You wanted to test the hypothesis that some exposure may be associated with the disease. You really want to try to understand the strength of that association and look for a dose response to look for causality in the relationship. The last type of occupational epidemiology is evaluations of interventions. And in these, you want to take some type of preventive action to reduce exposures or disease outcomes and measure the changes in the health status of your workers over time. Okay, this is kind of an overview of what you do in an occupational cohort study. These are really the gold standards for studying the association between exposure and disease. They're less susceptible to bias. In occupational cohort studies, you start with a defined group of people. In my studies, we started with manufacturing plants, workers at manufacturing plants. You follow them up over time to see at the end of your study who's alive and dead. You classify the workers by the level of exposures. You enumerate their causes of death, count up how many people died of lung cancer, heart disease, et cetera. And then you look at you calculate a measure of association between the exposure and the disease. An example of this is the standardized mortality ratio, which I'll explain to you how we do that. You can also calculate relative rates and other measures. So this is just kind of a cartoon of how you do a cohort study. First, you get two groups of people. You have an exposed group. For example, these are people exposed to chemical exposure. A non-exposed group, people who aren't exposed, or a referent population that's not exposed. And then you follow both groups up to see who got the disease. So in this one, there are two people in the non-exposed group that got disease and two people in the exposed. Then you compare the groups to see which group had the higher level of disease or higher rate of disease. So there are three possibilities. Both groups could have the same amount of disease. One group, in this example, the exposed group could have more disease than non-exposed group. And then in this example, the unexposed group could have more disease than the exposed group. So this is how you calculate the measure. Basically, it's just a ratio of what happens among the exposed versus what happens among the non-exposed. So again, you have your exposed and non-exposed groups. And your exposed, 2 got the disease. 2 out of the 12 got the disease. And non-exposed, 2 out of 12 got the disease. So they both have the same rate of disease, and you calculate the ratio, and in this example, it's 1.0. And this is an example of no association between exposure and disease. The rate of the disease in the exposed group was the same as the rate of the disease in the non-exposed group. And this is just another example. In this one, 8 out of 12 in the exposed got the disease, versus only 2 out of 12 in the non-exposed got the disease. So the rate of disease was higher among the exposed group than the non-exposed. And in this one, the ratio is 4.0. So in this example, there's a positive association between exposure and disease in this example. The disease rate in the exposed was 4 times that of the non-exposed. And here's the last example. In this example, only 2 out of the 12 folks in the exposed group got the disease. And then 8 out of 12 in the non-exposed group got the disease. So more people than non-exposed got the disease. And your ratio is 0.25. So this is called a negative association. It's less than 1. And in this one, the disease rate in the exposed was 1/4 of the rate in the non-exposed. So the disease rate in the non-exposed was higher when it's less than 1. So when you look at measures of association, they also calculate something called a confidence interval, and I'll show you some examples of confidence interval. And what you want to look for is if the confidence interval includes 1. Confidence interval is a probability level, or the likelihood that your true rate of disease, or what we're calculating here, is between the two numbers. And if it includes 1, then that says that your relationship is probably due to chance. It's not a statistically significant relationship, and I'll show you that as I go through the results. These are some different ways to measure exposures in occupational studies, from most precise to least precise. I mean, the best measures are actually to just do personal measurements of the workers. And then you can go to job area measurements, job-specific area measurements, rank the jobs and the tasks that the workers do, look at the length of employment in an industry for the workers, or the simplest measure for exposure is ever, never employed in the industry. And each of these, really, it's a measure of precision. So you go from the top and you get the most precise measures of exposure down to the bottom, which the never, ever employed in the industry is susceptible to a lot of bias. Okay, here's just a brief overview of how we do the analysis. I wanted to talk about the standardized mortality ratio. You'll see a lot of that in these type of studies. Really, this is similar to the ratio I showed you before. It just compares the mortality experience in the exposed to a non-exposed standard. And in these type of studies, the non-exposed standard is usually the general population, or either the state. In the U.S., it's either the state or the nation. These measures you can adjust for age, race, gender, and calendar. So as I put at the bottom there, it's really observed mortality over what you would expect in the general population. You could also do Cox regression analysis or other types of regression analyses. And these compare rates of the disease in the exposed to the non-exposed. And you do these type of analysis for the internal analysis. And in the internal analysis, you compare the rate of disease in a higher or medium exposed group to a lower exposed group. So you're just looking at the workers in these type of analysis. You're not looking at the standard outside population. Okay, this is just another cartoon of looking at the strength of association. So if your relative rate is less than 1, it's called a negative association again. Again, this is people in the exposed group have a lower rate of disease than people in the unexposed group. If it's greater than 1, it's called a positive association, so the exposed people have a higher rate of disease than non-exposed. And again, 1 means there's no association, so the rate of disease in the exposed and unexposed is the same. The next couple slides are some issues to consider when you look at study validity. One is the length of the follow-up, and in this one, it's the time from the date of hire until disease onset, death, or end of the study. And for this, it's important to follow up your cohort members for the furthest amount of time you can. If you just follow them up until the end of their work experience, they experience something called the healthy worker effect, where you're only studying them while they're working, not beyond their work. I'll talk a little bit more about that. You also want to try to understand duration of employment, which is correlated with cumulative exposure. Again, this could be a problem with the healthy worker effect. So the healthy worker effect has 2 aspects associated with it. And in this issue, it's the tendency for people who are working to be healthier than people in the general population. So you have to be healthy to work. Healthy worker effect, it's most pronounced right after people start working. So you have to be healthy to be hired. And these people are probably healthier than the people who aren't working. It's also present in workers that continue to stay enrolled. So to continue to work, you have to be healthy to work. There are a couple of ways to look at this in the analysis. One is to do a latency analysis looking at disease risk by time since first hired. There's lots of evidence that the healthy worker effect that affects workers right at their hired date it goes away after about 10 years. So if you're following people a long period of time, then this bias is lessened. You can also do internal analysis, comparing high exposure workers to low exposure workers. This way you're only looking at people who are working. You're not worried about the people who aren't working. You control for time since first hired in these analyses. You can also do something called a lagged analysis. And in these type of analysis, you remove exposures right before the outcome. Because typically in studies of cancer, it takes about 10 years for an exposure to cause a cancer outcome. So the 10 years prior to the cancer outcome really is misclassifying the exposure that the individual has. So if you remove those in the analysis, you can reconstruct your internal analysis to control for that. So we did all of these things in our study, and so you'll see examples of these. Okay, the next part I'm going to talk about my study that we did in the US. This was actually a really fun study for me. The data is very meaningful to me because I actually went out to the plants. I toured every plant with industrial hygienists. I talked to lots of workers, tried to understand their jobs and their health history. We looked at all the old records, the air sampling records. So it was really, the data is actually really quite meaningful to me. So the objective to this study was to understand the mortality experience of a large cohort of TiO2 workers in the United States. And we compared that to the general population in each state, and then we also did it by level of exposure to TiO2. So these are the internal analyses. These are the 4 plants that we studied in the US. So let's see, number 1, we went over to Hamilton, Mississippi, up to Ashtabula, Ohio. We were in Baltimore, Maryland, and then in Savannah, Georgia. So we actually had groups of graduate students that went out with me to collect all the worker hard copy information, and we scanned it and put it into a file. So it was quite a big effort. So this slide describes how we enrolled the cohort. So we identified everyone who'd ever worked at the plant through 3 methods. We used something called work history cards. They're called Cardex cards. And you see this across industry. It's really just the handwritten form of recording people's work. And I have an example, I'll show you that. And then about the mid-'80s, people started computerizing their employment records. So we got all the employment files. We also looked at all the retirement and pension records, as well as all the medical records, to try to understand or capture everyone who'd ever worked in these facilities. This is just a diagram to show you how many people we initially identified, and they fell out in the analysis, they fell out because of certain reasons. So we originally identified over 8,000 folks. Some of them didn't work at the plant, so that's 245. If people worked less than 6 months, we excluded them from the analysis. These people are different than people who work longer than 6 months. There are about 2,000 of those. If they didn't have complete work history, we excluded them because we couldn't classify them according to their titanium dioxide level of exposure. We excluded those that didn't have a birth date because if they don't have a birth date, we can't follow them up in the national records to see what they died of, if they were alive or dead. We also terminated those prior to 1960. We excluded those who terminated prior to 1960. The national health records in the US start in 1960, so we had to get rid of all those. So at the end of the day, we split them out into people who only worked at administrative jobs and people who worked in the production, and we had about 4,000 folks that we studied. So this is an example of the Cardex work history that I mentioned. You can see that this worker has information. I'm not quite sure how to work this. Let's see. Well, down at the bottom there, you can see that it has their identifying information so we can trace them, their social security number, when they first started working. And then down this side, it has this person worked as a packer, and then they did some rework, and I'll show you some more about those. So this person was pretty heavily exposed to titanium dioxide. So we imaged all of these, we brought all the images back, and then we digitized them, put them into a computerized database. So we followed every person up in our cohort, all 4,000 people. We linked them with national mortality files. And at the end of the study, which I think this study we followed them up to 2,000, we classified each member as alive, deceased, or they were lost to follow, which means we couldn't tell if they were alive or dead. And there were only about 3% of the people we couldn't find. The next couple of slides, I want to talk to you about the manufacturing process and how we did our exposure assessment. So at the plants, there were two types of processes, which I'm sure everyone here knows, chloride and sulfate. Two of our study plants only had the chloride process, and two had both chloride and sulfate. This slide just shows the production process. And really the main reason I wanted to show you is everything above milling and classification pretty much happened outdoors, and everything below happened indoors. So here are a few pictures of this. So this is kind of the chloride end of one of the plants, and you can see everything's outdoors. People are working outdoors at this site. Then as you go in, this is more of the milling and filtering process. As the TiO2 comes out, it's wet, and so they start drying it, and then they mill it down to whatever size they need for the application. Then in here, I don't know if you can see kind of behind the glass is the bagging. This is where the packers are packing up the different bags of titanium dioxide. This is one area of the plant where it's called the rework area. So sometimes the bags explode or other issues happen, and they scoop the titanium dioxide off to the side and put it back in the process. And this is just the warehouse with all the bags of titanium dioxide. I think one of the problems is, when the forklifts come in, sometimes they puncture the bags, and then the titanium dioxide goes out. So these are some pictures of one of the plants. So the next few slides, we talk about how we did the exposure reconstruction for the plants for each worker. First, through the Cardex cards and the computerized files, we obtained all the work histories, and we created something called a job dictionary. So from the work histories, we made a list of all the jobs that were ever held in each of the plants. And then we also categorized the time this job was first held and last held. And with this, we created something called a job dictionary. So then we went out to each plant, we talked to old-time workers, asked them about the tasks that they were doing with those job titles, and during those time periods, to really understand the activities, the task, and the different exposure potentials. We walked through the plants to look at process and ventilation changes. We got all the IH air sampling data that we could find. Then at the end, we created a job exposure matrix. And in this, we were able to classify each person. We were able to look at their level of titanium dioxide exposure by job title, by year that they were in the job, and location. And then for each person, we calculated a relative exposure index for each cohort member to understand their titanium dioxide exposure over time. This is just a slide of the titanium dioxide air sampling data in all the plants combined. And really, you can look from 1976 to 2000, the levels of titanium dioxide in the plants were getting lower over time, regardless if you looked at the mean, median, or geometric mean. For the job categories, you did see a differentiation by job title in titanium dioxide exposures. So the packers, the micronizers, and add-backs, rework people had the highest levels of exposure. There were also the maintenance mechanics. Those were the guys, if the pipes or other processes were clogged, they went in and titanium dioxide would come out when they were fixing the problems. So those were the highest level exposed jobs. So next I want to show you some of the statistical analysis. I'll show you the SMRs as well as the internal relative risks that we did. This is just some characteristics of our population, mostly men. A lot of them were white, born before 1950. more than half. Most of them worked 5 to 20 years, and most of them were alive at the end of the study. So here's some of our analyses by time since first hired and number of years worked. So if you look across the top there, so down the side, these are number of years worked, so we categorize them 0 to 9, 10 to 19, and 20 plus, and then down at the bottom is total. And then across the top is time since first hired, 6 months to 9 years, 10 to 19, and more than 20. So you can see the healthy worker effect in play here. If you look at the group 6 months to 9 years, and you just go down there, they're all healthier than the standard population. The relative risk the SMRs are less than 1. You can see that the confidence interval there, so that's the numbers in the parentheses. It goes from has a small to large. So this is the 95% confidence interval. And what this tells you is a statistical test to tell you that if you repeated the study over and over, 95% of the time your true value of the measure of association would fall between these two limits. And if it encompasses 1, if 1 is included in that confidence interval, like the next one down for all malignant neoplasms, these are called non-significant because it could be no association between exposure and outcome. You can see everything is pretty flat here, except for we do see a slightly elevated risk for lung cancer for workers who worked less than 9 years, more than 20 years ago. So we looked at this group a little bit more, so it was 1.5, and the confidence interval was 1.0 to 2.3. We looked at this group a little bit more, and we saw that only 2 of these workers actually had exposure to titanium dioxide. So this was really not a meaningful relationship here. We also looked by job categories as a level of exposure. So if you remember, packers and micronizers and add-backs, had the highest level exposures to the ore handlers, which had the lowest level exposures. And really everything's pretty flat. All the confidence intervals include 1. There's nothing really interesting going on in these analyses. I wanted to highlight the ones we're most interested in is lung cancer and non-malignant respiratory disease. Again, all the confidence intervals include 1, so there's nothing of importance going on here. Okay, these are internal analysis. We did quite a few internal analyses looking at time, different age scales. We did the lagged analysis, and again, all of these are flat. At the bottom, you can see something called a p-value, and that's a p-value for trend. And what this tells you is it looks to see if there's an increasing risk with increasing level of exposure. This is kind of a measure of dose response. And if the p-value is less than 0.05, then it means there's a significant relationship between the exposure and the disease. And none of these have an elevated p-value, a statistically significant p-value. Okay. I also want to talk a little bit about smoking. It's important to understand smoking in your cohorts, especially just because of a strong relationship to lung cancer. And this is just an example of showing the different causes of lung cancer. And smoking is attributed to about 83% of lung cancer. So it's really important to get some understanding of smoking in your cohorts if you're looking at lung cancer. We were able to look at the medical records and determine smoking status for a proportion of our cohort. This isn't everyone in our cohort. And we compared it to some CDC measures at the same time period. And you do see in this one that our cohort workers across all time periods did smoke more than what was found in the general population. And this is pretty typical. Okay, next, for my last 5 minutes, I'm going to go over the other studies. So this is the first 3 studies are the DuPont studies, and really they're similar cohorts. So it's the chain study is a little bit smaller, and then the 2 Ellis studies build on that. The Ellis study from 2013 is really a subset of the Ellis study from 2010. The 2013 study is a subgroup who has very detailed information on their job histories. So they wanted to make sure that they had good information. I think the interesting thing to look at here is that all of the studies, they looked at people who were employed for at least 1 month to 12 months, so we had different time frames to try to get rid of those people who quit right away. There's some variation in gender, some variation in race. The studies looked at different time periods, so the Ellis studies went back to 35. Bofetta, that's the European study, started in 50. We started in 1960. We had different periods of follow-up. The mean age at entry was pretty much the same. We all followed up our cohorts more than 20 years. And we had similar level of deceased population. We did also use different comparison groups. The Ellis study used both the US standard. They also used a internal comparison of other DuPont workers. And I'll talk a little bit more about that. And we used the state, and Bofetta used the country-specific studies. Okay, so here are some of the SMR analyses for selected causes. Really, everything looks pretty similar here in flat. It's interesting that the Ellis study, when they compared to other DuPont workers, saw an elevated risk. And the authors mentioned that this could be how their comparison cohort of other DuPont workers was constructed. What they did is prior to 1979, they used only pension workers at other plants, not the titanium dioxide plants, and active workers to construct their comparison group. And this is a healthy worker group. So it's not surprising that they see an elevated risk here for this. Again, when they compare it to the US standard, everything's flat. Okay, these are the internal analysis across all of these studies. People categorize them differently. They either looked at quartiles, quintiles, tertiles. So I just made a slide, just looked at the relative rates from increase in exposure as you go down. Everything here is flat. You don't see a relationship between increased risk of lung cancer with increased exposure of titanium dioxide. Some of the studies calculated a trend to show if increasing risk was related to lung cancer, and again, these were flat. So none of the studies show anything that's very surprising. Okay, conclusions. We studied over 25,000 titanium dioxide workers. The SMR analysis showed that lung cancer mortality was not elevated, except when TiO2 workers were compared to DuPont pensioners. I forgot to mention the Bofetta study, they did see an elevated risk of lung cancer, but in the external analysis, when they compared it to the different countries, but they thought that this was due to a couple of the plants had much higher smoking levels than the general population, so they thought this was due to smoking. But the internal analysis of all the studies, none of them showed a dose-response relationship between titanium dioxide and lung cancer. So the results are pretty consistent across the studies. Even though they're different time periods, they have different geographies, and this is really pretty strong evidence that there's no relationship. If you're looking at different cohorts and you're finding the same thing over and over. None of the cohorts saw a dose-response relationship with titanium dioxide and lung cancer. And finally, none of these studies support that titanium dioxide is related to lung cancer, to any type of cancer, or any cause of death. Okay, thanks.
That was very good, John. Thanks very much. Now,
thanks.
My question is, the French ANSYS document related to the IARC evaluation, which said there was inadequate evidence for carcinogenicity in humans, which I think is another way of saying negative. But there's one clause in there that said, but there were methodological limitations. And ANSYS used this to essentially dismiss totally all the epidemiology data. So my question to you is, what could those methodological limitations be, and why would they be so significant that they'd be essentially the whole data ignored?
Yeah, I mean, that's interesting to me because, as I said, we have, 4 or 5 different studies, and they have things like information bias and things like that, but it's different across the study. Not every study has those same type of biases. So to me, it's just stronger proof, even though they have these different biases, that you're finding the same result over and over. So I guess I don't understand that statement. Yeah.
Anybody else who might understand that statement, who might want to intervene on that point? Yes, both of you. Yes.
in your introductory part, you didn't mention plausibility. And, you know, we toxicologists are consumers of epidemiological studies. But what we try to do is to evaluate whether there is a plausibility. And in many cases, what we see from epidemiological studies like NO2 health effects at 20 micrograms, which are defined by WHO, or the diesel exposure studies where they extrapolate, the epidemiologists extrapolate from high to low doses, and then they predict lung cancer risk of 2 into 1,000 at 1 microgram per cubic meter, which is not plausible.
Yeah.
And whatever we say, they say, okay, we have statistical methods to be able to extrapolate from high to low and even predict for sure or precise risks at very low doses. And we say it's not plausible.
Yeah, I mean, for our study, we actually were able to measure actual exposure levels, and we did use those to try to understand exposures of the workers. So, yeah.
That was a nice overview, John. Thank you very much. Question, when you talk about those response analyses, which I would call exposure response analysis, were the categorization done by exposure concentrations at different workplaces, or how did you categorize those?
Yeah, so we were able to understand each person's exposure history, and then we were able to look at their exposure as it increased over time. So we were able to use that as a continuous variable in the model. So.
What's the basis concentration measurements at the workplace in the airborne state?
So we tried as best as we could based on a person's job title, their history, and actually the year that they were in the plant, because as you saw, exposures changed over time to develop what we call a relative exposure measure. So.
Other yes, 1, 2.
Yes, hello, Sylvia Jacobi from Albemarle. I have a question on your reference populations. You said you made it by state, but how do you calculate if people migrate from one plant to the other? I don't know if that happens, or can you, if sometimes you do meta-analysis of all the workers, how do you choose your reference populations then?
Yeah, so in this we didn't have any evidence that they migrated at all. But we tried to use the referent population, which is closest to what your worker population is. So you want to try to get the smallest area you can. There are some geographic differences, not only in terms of potential exposure, but like lung cancer or smoking rates are different in different states. The diagnostics of lung cancer different in different states. So you try to get it to as similar as a geographic area as you can. So that's why we use state instead of like a national population.
Okay, satisfied with the answer? Yes. We have another intervention at that side. Yes.
Christophe Roussel from ANSES. Just for clarification, you said, if I correctly understood, that you have more smokers in your study. So were you able to show an excess risk of lung cancer or mortality compared to the national population for these workers? Because you should expect to have a higher SMR for these kinds of workers due to tobacco. And then what is the power of your study? I missed that. Maybe you have presented that, but I missed what is the power of your study and what type of excess risk you could be able to show if there is any excess risk.
Yeah.
When you say the power of the study, you mean?
You mean the how many, usually when you do epidemiological study, you have an hypothesis on what is the excess risk you will be able to show when you calculate the numbers of people you have to include in the study. So yes.
Yeah. So I'm sorry, I didn't hear the first part of your question.
The tobacco, you said that your workers were more smokers than the other part of the population. So you should expect to have excess risk due to the effect of tobacco on lung cancers and mortality, and I missed that. But maybe
Yeah, so we didn't look at those workers by themselves, just because we were unsure of what that population was. It was just whoever information was recorded in their medical records had smoking in it. So it's some type of biased population that we didn't quite understand. So we just wanted an idea of smoking. So
what you're saying is that it should show up in the thing.
Yeah, they should show, you should have observed more lung cancers or mortality because of the highest numbers of smokers in your population. So that was my question. For me, you should have observed that excess SMR due to the effect of tobacco in your population.
Is that correct?
So as I said, we didn't see an excess of smoking in our population. I mean, excess of lung cancer in our population. That's just what the data was. I mean, smoking didn't seem to have an effect in this population. So you asked about power as well. When you conduct a study, after you've completed it, you don't really look at power. You look at the confidence interval to see the level of risk that you could measure in your study. So in this study, we had pretty good confidence intervals. They weren't wide; they were pretty narrow. So we had pretty good measures of association.
You satisfied with the?
Thank you. Yeah.
Yep.
Okay. Other interventions, comments, questions? Yes.
Robert Bird, Huntsman, Pigments and Additives. In your pictures you showed of the factories, there was some evidence to say some factories were more enclosed and more higher standards than others. Have you got any evidence to say that if the standards are higher or the mechanical interventions are better, you get improvements in or less effect to the results?
Yeah, so just to be clear, we didn't see any effect, regardless of how dirty the plants were or not. So I'm not sure it would be meaningful to try to separate that out. So.
Satisfied?
Could you have another look and see?
Pardon me?
Could you have another look and see?
To see if it was different by plant?
Yeah.
Yeah. Actually, you could do those analyses, but we didn't do them because we didn't. Yeah, we didn't.
It would be possible.
Yeah.
To have a look. Yeah.
Sounds like you're going to stay in touch, and might be a bit of a follow-up there. Okay.